set of types of waves develop. They're called Rossby waves. And these Rossby waves, they propagate westward. And so doing so, they propagate all the information, mainly energy, westward within the basing. And so what happens is that if you start with a symmetrical gyre, because of the differential rotation and the existence of Rossby waves, these will move the wind-driven gyres towards the west. And because of the existence of a continent or barrier or wall, then the gyre will squash to the west. And so the center of the gyre will be squashed towards the west. And so there will be an interior solution and a western boundary current on the other side. And the way you balance the flow and the input of vorticity by the Whistler's curl is through friction on the wall. So friction is the way to put the motion in balance. It's not the reason for the western boundary. And then we saw that you actually don't need that much friction if you slightly add complexity to the model. So if you add a sloping bottom topography, especially on the western side of the basin, then there is an extra term that is related to the pressure gradient and the slope of the bottom, which is called foam drag or bottom pressure torque. And this bottom pressure torque adds vorticity to the system as well. So you don't need friction to add vorticity to the flow as long as you have a sloping bottom. Okay? And so this sloping bottom, what does is to give vorticity to the flow so that it can change planetary vorticity and move in a subtropical gyre northward. So we saw that these particular flow induced by the bottom foam drag is parallel to f over h contours. So it's parallel to the contours of the depth of the basing times the Coriolis parameter. And so the flow doesn't need to be forced, doesn't need to be, this can be viscousness, frictionless. As long as there is a slope, then the flow will start to go down the slope and change f. So the input of vorticity is given by the slope. And so in an idealized case, we saw that most of the region of the western boundary current can change f, and so can have an input of vorticity through this bottom pressure torque. And the only place where you need friction is where you have to cross f over h contours, which is, in that simple case, on the southwest part of the basin, where f over h contours, they merge into a single point. So in that place, you have to cross f over h contours, and so you need friction. Then the flow can be free from force and friction, and can just follow f over h contours and go northward in that case. Okay? So you don't need that much friction in reality. So we were talking about the role of Rossby waves in the fact that you have a western boundary current. And so I thought of talking about waves that I should have before starting with the wind-driven gyres, I should have talked about waves. But we're going to do it now. Okay. So we're going to use the shallow water equations, which I think we know already. Okay, so we're going to develop the shallow water equations, and then from the shallow water equations derive all the wave type solutions from the shallow water equations. Okay, so we'll see all the kind of waves that you can get from the shallow water equations, especially on a rotating frame of reference. Okay. So why the shallow water equations? Because the shallow water equations are a very useful approximation to geophysical fluids. Main approximation is that the length scale of the phenomenon is much larger than the height or depth of the flow, which is a good approximation. And shallow water equations are very useful because you get rid of the dependence of depth. Okay, so that's good. but we're going to keep a surface elevation anomaly where waves can develop. Right? And we're going to use the hydrostatic balance. And we are going to use a single homogeneous layer. Okay? You can do the shallow waters in end layers, of course, okay? And get end modes in the waves. So you can generalize this easily. Well, we're going to do it for a homogeneous layer. Okay, so let's see what the shallow waters are. Same thing as in the ocean, of course, as in the atmosphere, of course. You say shallow water equations in the atmosphere literature as well, right? You do. That's good because in oceanography we use the thermal wind from the atmosphere, even though the currents. So at least atmospheric physicists they use shallow water equation. Anyway, some revenge. So we're going to use a very simple homogeneous layer of total depth h, where there is a surface elevation eta, okay. And this is going to be small h. Okay, so one single layer of rho naught. Of course, the condition is that the length scale is much larger than the depth of the fluid, and we use the hydrostatic balance. Okay. Z is going up from z equals 0 to eta. So our pressure, which is going to depend on x, y, z, and time, is going to be minus rho g z plus p naught. Okay, but of course the pressure has to vanish at the surface. Okay, so p has to be 0 at z equal eta, so that P equal P naught plus P prime equals 0 at z equal eta. So this leaves our P prime as rho g eta. Okay, and if you take the gradient of this, the horizontal gradient, this is going to be dropping P prime. So the gradient is independent of z, so that's the important thing. So the only variable that we're going to keep is the surface elevation, where the waves are going to develop. Right? You could do this in n layers within the ocean. It doesn't matter. Okay? So our momentum equations are going. So the horizontal momentum equation. So U is now U and V, okay? It's only the horizontal momentum equations. Graph P, and if we substitute that, it's minus G. Okay. So there's no dependence on Z. That's the nice thing about the shallow water equation because of the main assumption that L is much larger than H. So L has to be much larger than H. And of course, if you add rotation, which is what we're going to do, these are going to be the horizontal momentum equation in the shallow water approximation. Okay, so this is the horizontal momentum equation in the shallow water approximation. Now we have to work on continuity. Okay, and work on continuity in the shallow water equations. So we can do this from first principles, as we did in fluid mechanics, conservation of mass. We're going to do with some surface elevation beta.
Professor Farneti, Massimo here. Just could you please check on the monitor while the black body is in the frame, because I've moved the camera on the left, because usually it's on the right side. In the monitor, or the computer monitor. You can see what we can record and what the people at home can see. Yeah, from there
Yes, you can see
to the two blackboards complete.
So
okay.
I have to stop here.
Yeah, thank you. I have moved the camera on the left just to let you.
Okay, thank you.
You're welcome.
So we can derive the continuity equation from first principles, where now this height of a fluid column within the shallow water is h plus eta. Okay, so this is h plus eta. This is some delta x, and this is some delta y. Okay. So if there is a mass flux through our column of fluid, in and out, and so the mass flux is going to be in the x direction, is going to be rho u times the area. Okay, and the area is rho times u, and the area is h plus eta. Delta y. Okay, so that's going to be the mass flux in and the mass flux out. So whatever comes in is rho, not to make any mistakes, u minus half, so from the center h plus c u dx dy minus, yes, and what goes out is same thing, plus. Okay, just doing continuity on a shallow water column of fluid. And so if you make the difference of this is simply delta x, delta y, d by dx of rho u h plus theta. Okay, that's just the difference of the two. And so if you consider the other three faces, the total net rate of change, as we did in GFD, so the total rate of change is going to be d by dt of theta the total height of the fluid equal to 0. Okay. Now you could do two things. Depending on the way you prefer to work, you could substitute h plus eta with small h. So you could work with u which is this, or you can make the assumption that eta is much smaller than the total height h. And so if you do that from here, which is it's just a matter of how you prefer to work. Okay, so this is going to be continuity in shallow water. So if you start working from this h, what you normally do is you only want to work with h, okay, so let's start again. Can remove this. If you retain eta, then what you do is you linearize on a state of rest, so that u is u naught, which is 0 because it's state of rest, u prime, and then h is h plus eta. So that you get and if you remove or if you neglect higher order terms, then you get to that. Just to get rid of higher order terms, this one as well, then you recover the same continuity equation. So it doesn't really matter if you start from this assumption or if you then linearize on a state of rest. So these are going to be the shallow water equations that we're going to use. And we're going to look for wave solutions to these equations. Ah, there's the snake. but I lost the chalk. There you go. That's correct. Made a mess. Okay, so we're going to look for wave solutions. And we're going to look for dispersion relations. Okay, so we're going to look for the dispersion relations of all the different solutions. We're going to look for the typical solution in this case, so that U, V, and eta solutions are going to be I, 3x plus y minus omega t. Okay. We're going to substitute this kind of wave solution into our equations and see what we get. Okay, so we're going to have some d by dt, d by dx, and d by y. Okay, so all the d by dt of u, v, and eta are going to be minus u naught, v naught, naught, then the I omega, I kx plus Ly minus omega t. Then we have some d by dx of u, v, and eta. And these are going to be u naught, v naught, eta naught, dxik. And all the d by dy of u, v, and eta. Are going to be of this I L I x plus y minus t. Okay. So now let's plug those wave solutions into our momentum equation, and you're going to get minus u naught I omega minus f naught naught. At some point I will drop the naught without even noticing. Minus v naught I omega plus f naught naught I L, and then the continuity equation H I k u naught plus I L v naught equals 0. Okay, so this is a system that admits solutions only if the determinant is equal to 0. So the determinant of this system is naught plus gik, and then minus omega plus naught gil I omega h because I have to put the U here. Sorry. So it's I, K, H, I, L, H, I, omega. So the determinant of this is to be 0. And so there is a mistake here as well. Okay, UV eta. UV eta, and so the determinant of that has to be equal to 0. So now you look for solutions of the determinant, and it's going to be this minus h k squared g. So square minus omega g. Already a GH coming out that should ring a bell. This is this minus f naught squared minus GH. Square equal to 0. Okay?
You have substituted in place of the Lagrangian derivative now, there is just the time derivative because the perturbation gives rise to second order.
Yes. Okay, so now there's a few solutions that are admissible here. Some are trivial and some will give rise to R waves. And I will start by drawing my wonderful dispersion relation here. Okay. So the first solution is obviously frequency equal to 0. Okay. So that is an arrested wave. Okay. No wave propagation, so it's a time-independent flow. And if you put frequency equal to 0 back into our equations, look at the horizontal momentum equation, that's just a dystrophic flow. Okay, so dystrophic flow can be interpreted as an arrested wave. In fact, I'm not going to do it, and I guess you didn't do it on straight wave, but if you look at the typical example of adjustment in a rotating flow from a perturbation, there is an adjustment from rest, an eventual balance of the flow between the pressure gradient and Coriolis, okay, and giving rise to dystrophic flow, dystrophic balance. Okay. So that can be interpreted as a first initial response of a wave that then is arrested at the dystrophic balance with a certain length scale that is given by the Rossby radius. Okay. So if you think about dystrophic flow that way as an adjustment process, then you can think of an initial wave that then is arrested at the dystrophic scale of the Rossby radius. So in our dispersion relation diagram, this is the first solution. Okay, the dystrophic flow. Frequency equal to 0. Trivial, but it's one of the solutions. Then you have the second solution, which is slightly more interesting, which is that this has to be equal to 0. So this equal to f naught squared plus gh a squared plus n squared. Or where C is GH, the phase speed of a gravity wave. So this is the second solution, and as you can see, the frequency is always larger than the Coriolis frequency. So these are waves that are super inertial. The frequency is always larger than f. And these are the general solution of Poincare waves. Also known as gravity Poincare waves. In the limit of no rotation, so that f naught is equal to 0, then the frequency is this. So this is a typical gravity wave of phase speed c. But there are two of the general Poincare waves. There are two limits that are more interesting for us on a rotating frame of reference that would make me start writing this. Okay, but actually I can write here. So the okay, so I'll draw this. So the no rotating case. The no rotating case is going to be this. And the slope is given by the phase speed c. That will be this. If you take the full Poincare solution, actually you have a first case that is the short wave limit. Okay, so if the wavelength is small, so k is large, that means that big kappa here is much larger than f naught square over gh. Okay, so in the short wave limit, wavelength is small, wave number is large, so this is much larger than f naught over c square. Okay, and so we can neglect this, and so we can neglect f naught, so that we have that the frequency is again c square k square. So it's again the same dispersion relationship as a no-rotating case. So we are in this limit, okay? Short wavelength, large wave number. So the Poincare wave will asymptote to the case of a no-rotating gravity. So even though there is F, so it is a rotating system, but for small wavelength, yes, for small wavelength, it doesn't feel rotation. It's just a gravity wave. And you can see that because if you substitute kappa with the wavelength, you have 2 pi square over the wavelength squared. That is much larger than f square over gh. Okay. So this means that 2 pi over lambda much larger than f over gh. Which is C. Okay, so lambda is gh squared root over f 2 pi. And what is this? So the wavelength is much smaller than the raspberries. Okay, so the wave is too small to feel rotation. Rotation is existing, okay, but the wavelength is too short compared to the raspberries. So the wave doesn't feel rotation in the short wave limit. So we are somewhere here and somewhere here for very long wavelengths. Then you have the opposite case of long wavelength. So the condition is opposite. K square is much smaller than f naught square over gh. Okay. So this term is small compared to f. So the dispersion relationship reduces to this in the long wave limit. And this, again, if you make the same analysis, is scale analysis, because lambda is much larger than the Rossby radius. Okay. So if you make the assumption that kappa is very small, and if you go back to your momentum equations, then you will see that you are in the limit that small kappa, small l are equal to 0. So there's no dependence in space, in the horizontal space, because the wavelength is very large and so kappa is very small. And if you go into the continuity equation, you will see that eta is going to be 0 in the long wave limit. Okay, just making this approximation. So this is a wave. Well, it's a solution that doesn't have a space dependency in KL, and eta is equal to 0, so it's not really a wave. Okay. And the solutions of the momentum equation are actually going to be something like this. In the very long wave limit. And these are called inertial oscillations. So the movement oscillates because we look for a wave solution, and they oscillate at the inertial frequency f, which is here. I was looking this morning for a way of showing it. Actually, in the ocean you can find inertial oscillations. Maybe not that easy, but you can find it. Okay. And so basically you see, if you trace a particle in the ocean, this is not seen. You trace a particle in the ocean with some instrument, sometimes you see that they looking from the top. Okay, there's no movement as a wave because eta is equal to 0. But if you're looking from the top on the x-y plane, latitude, longitude, whatever, sometimes if you follow Lagrangially a particle in the ocean, you see that it flows this way. Okay, and the frequency is the frequency, the oscillating frequency is f. And these are called inertial oscillations. And so the solution that we find is this. So a flow that oscillates at the frequency of f, which is going to be here, plus f. And actually we could draw the same here for minus f. Okay. So this is the other special case. These are inertial oscillation in the dispersion relation diagrams. Okay. So we found the first solution is a trivial one. No frequency equal to 0, and that's just trophic flow that lies here. Then for the full Poincare wave, there is one case in the limit of no rotation, which is no rotating gravity waves, which is this solution. Okay. For the non-rotating case. If you retain rotation, then you have two limits, the short wave limit and the long wave limit. In the short wave limit, so large wave numbers, you approach the non-rotating gravity wave solution. And in the long wave limit, you obtain inertial oscillations, which are here and here. Okay? So short wave limit, you approach this, and long wave limit, you approach inertial oscillations. So if you actually look for the full Poincare wave dispersion relation, you will find something like this. Okay, so here I'm supposed to asymptote towards the no-rotating gravity waves. Here I reach the inertial oscillation solution. And then for negative kappa, I again asymptote towards the no-rotating gravity waves. So these are the nice Poincare waves. Okay. You can actually do the same exercise with shallow waters on the equatorial beta plane, and you find similar kind of waves, but with a different beta plane on the equator. Okay, so Poincare waves are a nice solution, but not that useful, I would say, for a geophysical fluid. Okay, at the equator they are more interesting, but not at mid-latitude. Not much. Okay. So now we're going to look for a different solution that is much more interesting for ocean dynamics, but also atmospheric dynamics, which are Kelvin waves. Okay, so now we're going to, with the same set of equations, we're going to look for a different solution, which is the one given by Kelvin waves. We'll see that Kelvin waves are, well, not Kelvin waves in the atmosphere, same thing in the ocean, and but you'll see that Kelvin waves have a lot of importance in the ocean for mid-latitude, the equator, coastal upwelling, and even tides. Okay, tides are coastal, are Kelvin waves. So we're going to look for Kelvin wave solutions. The way of getting Kelvin waves, you need a few. You need a few assumptions first. So let's make this my x direction and y direction. And let's say that there is a wall here, some barrier. It could be a physical barrier, or it could be a waveguide like the equator. And first assumption is that u is equal to 0 at x equals 0, of course. Okay, so no normal flow at the boundary. And what log Kelvin said is that, okay, if I start from the assumption that u equals 0 at x equals 0, then why not saying that u is equal to 0 for every x and y? Okay. So u is going to be 0 everywhere, whereas v is going to be different from 0, even at the wall. Remember that there is no viscosity. This is a frictionless shallow water system. Okay. So there's no viscosity, so v is different from 0 everywhere. So our shallow water equations reduce to this. dv by dt and dt is h dv by y equals 0. Okay, I just made u equals 0 everywhere. Okay, so now let's look for a solution for v eliminating the surface elevation eta. So if this is 1, this is 2, and this is 3, I take d by dy of 3. Sit down. I'm old. Okay, so if I take d by dy of the continuity equation, okay, if I plug this, okay, so this is d by dy of 3. Now I plug this into 2, which is 1 over g dv dt dy. Okay. So, oh no, sorry, I use this into the continuity equation in order to eliminate eta. So this is the d by dt of 1 over g dv by dt. Is it? Yep. Okay, so I use this d by dy of eta in here. And I get this expression for V after eliminating eta. And this is again C, okay, the phase of a gravity wave, phase speed of a gravity wave. So we know that these Kelvin waves are going to have a phase speed that is the same of a gravity wave. So Kelvin waves are going to travel at a phase speed that is the same of no rotating gravity waves. So you think, so where is Coriolis come into place? Coriolis will come into place because the scale, the horizontal scale of the Kelvin wave will be given by the Rossby radius. So that's how Kelvin waves are affected by rotation. The phase speed is the same of a gravity wave, but rotation is important for the horizontal scale of the wave. Okay, so we look for solutions of that equation, and we're going to look for a solution this way, 1 minus b. it doesn't propagate in X. So you could actually build this example, which you will find in many textbooks, as a channel. Okay, so I am looking at so if this is X, yes, okay, this is X and this is Y, and I'm saying that this is the only boundary at Y, and there's going to be a wave propagating. X, U is going to be 0, V is going to be different from 0, so there's going to be a wave propagating in this direction or in this direction. Okay. We could have actually build a model on a channel. Okay. So that you have two walls, meridional walls, one on each side. So you can allow solutions for waves traveling along this boundary and waves traveling along this other boundary. Okay. And we will see that this is actually a nice application of the Kelvin wave. But let's use just one meridional boundary. Okay. So U is going to be equal to 0, V is going to be, so this is my small v. Okay, so it's going to be a meridional velocity, and the wave is going to propagate along this boundary, okay, or along this boundary. If you have two boundaries, there's going to be two solutions, V1 and V2. So the wave is going to propagate along that boundary, and cancel the momentum equations, but actually the horizontal momentum equation for V was this, right, of course, right? That was the horizontal momentum equation for the meridional velocity, and now we can substitute that wave type solution into the meridional velocity momentum. V1 KC sine of K1 minus T, and the second solution is V2 KC sine of K1 plus CT, and that has to be equal to minus so I can write this one KC over G plus V2 KC over G sine of K plus T. Function of y. And so this is going to give me a solution that is minus. Yes. So d by y is going to be V1 KC over KG cosine of K 1 minus CT minus V2 KC KG cosine this kappa goes away. Okay, and so this is just a propagating wave as a function, well, described by the surface elevation eta. And we have two possible solutions there. As you can see, there's no F, so there's no there's no rotation. So this is the expression for the surface elevation. Now let's look for an expression for the meridional velocity. Okay, so we go back to the zonal momentum equation. That was minus Fv minus g d eta by dx. And so if that's the meridional velocity, the momentum equation for the meridional velocity, you see that is intrastrophic balance. Okay? And so the velocity is in balance with the pressure gradient. So it's intrastrophic balance, although it is moving. Okay? So it is a wave, but it's intrastrophic balance. And the balance is achieved, as I was saying before, the balance is achieved at a certain horizontal scale, which is going to be the Rossby radius of the formation. We substitute V in there, okay, and you can have fun doing it. So after a while you get to this expression, cosine k1 minus ct minus f(v2) k y plus t, and this is equal to, there's a d by dx, so that is going to be equal to minus d1 dx c cosine k y minus ct plus v2 x c cosine k1 plus t. I think so, if I didn't lose any minus sign somewhere, but anyway, you just substitute v there. And so you have these two solutions, V1 and V2, and you can look at the type of these two solutions. So one is going to be FV1, this, equal to C1 by X, this first part, and there's a minus, no, and the second one is going to be Okay, so they differ only on the sign, which is going to be crucial. So the first one is going to be 1 f over c by dx. And this is going to be 2 So the first solution is going to be V1 f over c x meaning that V1 is F over C, V1 is E to the F over Cx, and the second one is just the opposite. So V2 is E minus F over Cx. So one solution, V1, is growing exponentially with x, and the second one is decaying exponentially with x. Okay. And F over C, of course, is 1 over the Rossby radius. Okay. So this is E, put it x over L, and this is E minus x over L. So one velocity is exponentially growing away from the boundary, this V1, okay? And that is not a viable solution, okay? Because it cannot grow infinitely. Whereas the second solution decays exponentially away from the boundary, and the e-folding time scale is given by the Rossby radius of the formation. Okay, so the wave is trapped by the solid boundary and the Rossby radius of the formation. That's where the rotation comes into place in Kelvin waves. Okay? The phase speed is the same of a gravity wave, so it's not affected by rotation. But rotation affects the special scale of the Rossby radius of the rotation affects the special scale of the Kelvin wave. So if you're actually good at drawing, you will be able to, I'm going to make a huge mess. No, it's terrible. Imagine a wave traveling along the boundary, and the amplitude of the wave is decaying with an e-folding time scale that is equal to the Rossby radius of the formation. I'm in a mess. So this is not a possible solution for a wave. So our solutions, if we take V2, the second solution, our solutions are going to be V equal E minus x over the Rossby radius cosine, okay, y, and that was plus CT. U is going to be 0. We said that from the beginning. And eta, if we substitute the meridional velocity with the second solution, so the surface elevation is going to be given as C over G. So C is the phase speed of a gravity wave, cosine of K1 plus CT. Okay. So if you want to solve numerically and produce a nice map of a Kelvin wave, you just need to use this solution. So why Kelvin waves are interesting? They're interesting, so we said they are trapped. They are trapped by the meridional wall. The meridional wall could be a coast in the ocean, okay, for example, or it could be a waveguide like the equator. probably seen with Fred Kucharski that if you are at the equator, if you have looked at the El Nino, how do you form El Nino? Well, you have Kelvin waves propagating along the equator. So this is a Kelvin wave in the northern hemisphere, and this is a Kelvin wave in the southern hemisphere. And then you have actually radiating Rossby waves from the coast. Okay, so you have Kelvin waves that are trapped by this meridional boundary and the Rossby radius of the formation. They decay exponentially away from the boundary. Okay. And the exponential decay is given by the Rossby radius. For positive F, so if you go back to your equations and you look for positive F, so for F equal positive, the wall is left on the right. Okay. So in this case, the wave would travel in this direction. V would be negative. And if you put F negative in the southern hemisphere, the wall, the boundary, is left on the left, if you look at the solutions. So yes. So what was I about to say? Oh, tides. So if you look at the example of a channel in the northern hemisphere, and the walls are on either side, y equals 0 and y equals L, whatever, and you develop Rossby waves, for positive F, then your boundary is left to the right of motion, so V is going to be, in this sense, negative. And there will be a second solution, if you put two walls, that will give you another wave that leaves again the boundary on the right. Okay? So if you repeat the exercise and you put two boundaries and you make a channel, you will have two waves, one propagating in one direction and the other one propagating in the opposite direction. And so you have four different solutions, V1, V2 for one wave, and V1 and V2 for the other wave. Only one of the solutions is valid, so this wave decays away from the boundary, this wave decays away from the boundary, and they met at some point. And so this wave will travel with his own boundary to the right, and this wave will travel with his boundary on the right. And what you get is two Kelvin waves traveling in opposite directions that decays towards the center, where the surface elevation is equal to 0. And this is what a tide is, okay? A tide in a channel. I will show you tomorrow a map, a very nice map of the Adriatic Sea, actually, here where we are. So the Adriatic Sea is something like this. We are here. Okay. And is a nice laboratory, the Adriatic Sea, for geophysical flows in the ocean, because it's relatively small and has relatively the shape of a channel. And there are tides developing, of course, in the Adriatic Sea. And what you see are Kelvin waves traveling along the coast of Croatia, northwards, because the boundary has to be on the right, and Kelvin waves traveling along the coast of Italy, southward, because the wall has to be on the right. And this point, where the surface elevation is equal to 0, is where these two waves decay exponentially, and the tide grows and decays as a Kelvin wave around this point where eta is equal to 0, and is called an amphidromic point, where the tide is equal to 0. So the tide in the Adriatic Sea goes around this way as a Kelvin wave propagation. So a tide is Kelvin waves in a channel. The phase speed is that of a gravity wave, and the trapping length scale is that of the Rossby radius of the formation. Okay. If you take any textbook, some textbook they develop Kelvin waves with one wall because it's easier to see, but some actually start from scratch with a channel. So you get two waves developing, one in one direction and the other in the opposite direction. Okay. And if you look for solutions for both waves, one is valid, decays away from the boundary, the other one doesn't. And so this decays from the boundary, this other decays from the boundary, and you get this very nice wave solution of one wave traveling opposite to the other with an amphidromic point in the center. And that is nothing but a tide in a channel. Okay, so you can imagine that you form a lot of Kelvin waves in the ocean as long as you have a boundary, a coast, and you have some perturbance at the surface that generate an initial disturbance. Then you can generate a Kelvin wave that travels along the boundary. I'll stop here and we'll do Rossby waves tomorrow. And I'll try to make some noise. So we decided how the exam is going to be. We're going to go for a single exam, okay? Because last year we actually did, so Gacic did an exam for his part first, and then we did a second exam. We're just going to do one single exam, 2 or 3 questions each of us, written. Unless they close us again. And so it's going to be at the end of the course. Bye. Bye-bye. Devo dire una cosa. Mi hanno fatto cazzettone stamattina, non puoi venire.
Non posso venire?
No, e io ho detto, ma cosa? Devi venire in classe e fa, ma perché le regole sono ancora che chi può entrare nell'edificio è solamente i dipendenti del CTP. Così controllano chi esce, chi entra, perché ogni volta che entri passi il badge e sanno chi entra e chi no. E vabbè, deve venire ancora una decina di volte per l'esame. Però perché lui sì e gli altri no.
io non sapevo questa cosa, per
E
quello.
neanch'io non ci avevo neanche pensato. Mi hanno detto, guardi che il tratto 1 che non è un dipendente ICTP, ho detto, vabbè, seguo il corso.
E poi solo quest'anno, perché l'anno scorso...
Ma no, ma per
Covid,
per
sì, no, no.
ancora per questioni di Covid ci sono ancora queste restrizioni che l'accesso all'edificio è garantito solamente ai dipendenti ICTP, no? Oppure l'idraulico che deve venire una volta viene, no? E quindi
Seguirò online,
Sì,
mi
mi spiace.
Sì, non è un problema, più che altro comunicherò oggi perché dovrei avere anche lezioni col professor Tompkins e comunicherò con lui che non posso venire a non seguire le lezioni.
aspetta, allora tu non di niente, io adesso mando un mail e dico questi qua sono studenti di università, devono venire, basta che ti registrano ogni volta che entri, che problema c'è.
Sono ancora assinato.
E allora? Vabbè, che non fa niente ti faccio sapere io.
Ok, allora quindi...
Quando è che c'è l'azione con
pomeriggio?
Tompkins?
Alle 2.
Oggi? Vabbè, ormai sei entrato, non uscire.
Ma stiamo in Adriatico giù, siamo in grado di informatica.
Ah, sì, vabbè. Sì, dai, ti faccio sapere oggi.
Ok,
Se avviamo ufficialmente il permesso. Sì, perché sennò è una stupidaggine.
Sì, più che altro perché la lezione di oggi in aula di informatica non viene registrata, quindi perderei
No, appunto.
4 ore. Grazie mille. Scusa il disturbo.
Figurati.
Appena scese fuori libero perché ci sono 2 venerdì.
Che deve andare a Diploma una prova.
Ok, deve andare a i biglietti europei a Roma l'anno scorso. No, però deve fare l'esame. Devi essere fare l'esame.
No,
E quello è l'11 giugno, però ora non lo so perché mi sorteggeranno, perché hanno messo la terza del 5%. Io ce l'ho il biglietto, però
gli altri ce l'hanno.
ce l'hanno anche gli altri, e l'Olimpia era il 25.
E vabbè, fammi sapere se ti sorteggiano e puoi andare, così metterò l'esame l'11 giugno. Così non c'è.
Non del cielo, perché deve stare lì a
Se non ci posso andare io, c'è anche.
Ciao. I want you to avoid